Welcome. Welcome to Module 1, Part 0. And it's assumed that everybody here has taken Thermodynamics ME 350, the first course in thermodynamics. Here we'll just review a little bit from Chapter 2, governing equations, especially mass balance, energy balance, and entropy balance equations. These are all covered, the section numbers where you can find more info from the textbooks are mentioned in the parentheses here. We'll not rederive these equations. Instead, we'll go over the meaning of each of these balance equations. So let's start with the mass balance equation. The red boundary here is showing any system. System means any entity with a boundary. So the mass can come in, mass can go out with the different inlets and different exits. And the mass equation simply means the rate of change of mass within this boundary is due to the rate at which mass comes in, the net rate at which it is coming in, minus the rate at which it is going out. Mass cannot be created or destroyed. It's a very familiar equation. And a couple of things we got to remember about mass equation. Let me write those equations down here. Mass of a closed system is given by rho times volume. We all know that. Kg is mass. Kg per meter cube times meter cube. Right? Recall that capital V, we cross it to mean volume. Also, density is 1 over specific volume. What is small v? Specific volume expressed in meter cube per kg. It's the inverse of density. It's a thermodynamic property. So as far as thermodynamics is concerned, specific volume is it's a thermodynamic property versus density. Also, another formula that comes handy is m dot equals rho a v. That v means velocity. So the unit here is kg per second. You can just show that. So if there is a flow going through a tube, m dot, the mass flow rate, is given by rho a v. So from the get-go, remember that the specific volume v, the velocity v, and volume v, many times students get confused over these symbols. So make sure anytime you have a mass conservation equation in your mind, these formulas you got to instantly remember and keep it clear in your mind. Very simple formulas, very handy formulas, but they're used over and over again. Okay, let's turn into the energy equation. Again, this is a screenshot from the animation as shown here. 0D stored energy. The stored energy is given by the symbol capital E. In the definition of stored energy is the sum of U plus KE plus P. You got to memorize that. And then let's try to understand the meaning of different symbols. Stored energy is given in kilojoules. That's the standard SI units. EU, KE plus PE. KE and PE are easy to understand. K is the kinetic energy. Everybody knows that. Half mv square. Or in our SI units, it should be half mv square by 1000. So we'll write it like this. And PE is mgz. Again, we'll divide by 1000 to get the unit of kilojoules. KE and PE are organized energy of molecules. In other words, you can see this in your naked eye. If something is moving faster, you can say it has higher kinetic energy. If something is a higher elevation, you can say it has more potential energy, gravitational potential energy. On the other hand, EU, capital EU, is the sum of all the aggregate of all the kinetic and potential energy of the molecules. These are disorganized energies. So these are the energy of the molecules. So if you can understand what is KE or PE, you understand what is capital U, because internal energy is the same thing applied to molecules. just like Ke is reflected in the velocity, Pe is reflected in the elevation, U is reflected in the temperature, mostly in the temperature of a system. If the temperature is higher, you can immediately say it has higher internal energy. Sometimes the internal energy can be increased because of the potential energy of the molecules. For instance, if ice melts, then temperature doesn't increase, but still the internal energy increases because the potential energy of the molecules increases. Anyway, we don't have time to get into the details of that in this class, so please go and review chapter 0, 1, and 2 based on the background you possess. You have to be able to instantly write energy, what it means. Capital E means U plus Ke plus Pe. At the same time, if you divide by the mass of the system, then we can write small e equals U plus Ke plus Pe. So this is specific stored energy in kilojoule per kg, and this is all specific, corresponding specific quantities. Ke and Pe, the lowercase letters indicate kinetic energy per unit mass, potential energy per unit mass. Well, the conservation of energy basically means energy cannot be destroyed or created just like mass. So you got to figure out how the energy of a system changes. So let's go look at different mechanisms. Heat transfer is the first way in which energy of a system can be changed. Again, this is an animation. You can go and check that out. And chapter 2, in fact, chapter 0 goes over heat transfer in your textbook. And the important takeaway here is that heat transfer is given by Q in kilojoule or Q dot in kilowatt in rates. And it is heat transfer is driven by temperature difference. Whenever there's a temperature difference between a system and surroundings, there will be a heat transfer. Heat goes from high temperature to low temperature. We all know that. Important thing here is to understand the Wien-Hip sign convention. The different mechanism of heat transfer will be covered in a different class, heat transfer class, but it is not necessary to understand details of how heat is transferred in thermodynamics, except to understand the reason behind it. Whenever there is a temperature difference, it drives the heat transfer. If energy goes from point A to B, just like it through radiation, it comes from sun to earth, or conduction when you touch a hot surface and heat is conducted, or convection when hot air rises and carries energy with it. All these mechanisms are different forms of heat transfer. And the sign convention Wien-Hip means work in negative and heat in positive. That is, when heat is added to a system, we call it positive by convention, and when heat is taken out of the system, it's called negative. We will see the use of sign convention, which will become very important when we build the energy equation, because Q will enter the energy equation as an algebraic quantity. Another way to transfer energy from place A to B is through work. Well, the comprehensive definition of work is given here. The W dot or W dot is in kilowatt and W in kilojoules. W dot is made of external work, which is the one that is used mostly. Most of the time you use this one and something called flow work. The external work is made of things that are very easily identifiable, like a shaft work. It carries energy from point A to B. Energy, if the shaft is being driven by a blade here inside the system, then work is coming out. On the other hand, you might be twisting the shaft to churn this fluid inside, then in that case shaft work will be going in. Anyway, all these arrows here are in the positive direction of work transfer. Again, work in is negative, work coming out is positive. So shaft work is easy to understand, and everybody should know the shaft work formula, which is 2 pi nt. T is the torque, and n is revolution per second. 2 pi is the angle in one revolution. So this is just force time distance, as you know, counterpart of force time distance is the work, and force time velocity is the rate of work. So you can see shaft work comes from here. Force is replaced by torque and velocity is replaced by angular velocity. The electrical work, we are all familiar with the formula VI by 1000. If it's volt, it is amp. Then we have to divide by 1000 to get kilowatt. And boundary work is given by integral PDV, again a very familiar formula. And this is the rate of boundary work. Finally, the flow work is whenever a flow is pushed into a system, or a system pushes a flow out, work is done at the intersection. But we'll see that the flow work will be accounted for in a different manner, so that we have to only think about the external work in most situations. So what is external work? In short, you just look for if the boundary is moving, there is boundary work. If there is through the boundary there is an electrical current passing, you say there is electrical work. If there's a shaft turning, carrying torque, you know there's shaft work. So external work is very simple to identify. All we have to remember, when the work comes out, it is positive. When it goes in, it's negative. Well, finally, the energy can be carried by a flow. It's a little bit more complicated. First of all, it can be carried by the stored energy carried by the mass flow. As again, it is an animation. You should go and look at all these different modes that is shown here by clicking these radio buttons. But the summary is this: whenever there's a flow, it carries energy because of several reasons. Number one, it carries energy because energy is stored inside the mass that is flowing through it. We know E dot, the energy that is carried by the mass, is given by m dot times E. Small e is the energy per unit mass, and m dot is the rate at which mass is flowing. So it's reasonable to understand m dot times E is the transport of stored energy. The other term we add here is the flow work. Flow work, W dot F, is what? Because of the pressure pushing the flow in, the force times velocity, and you can show force times velocity. Force is pressure times area and velocity. And then you can show that this is nothing but pressure times area divided by density times velocity. And as you can see, this is rho AV, so it becomes m dot, and 1 over density is specific volume. That's how it turns into this simple term. And together, this is called J dot, the rate of transport of flow energy. So the summary is that whenever you see a flow moving in or out, it carries energy. How much? The answer is J dot. And look at how it simplifies, is m dot times E plus PV, and E plus PV together is called J, the specific flow energy. So if we have to simplify how much energy a flow is carrying, this is how we'll write an expression. We'll say, suppose here is a flow, we'll say the energy carried, the mass carried is m dot equals rho AV. We know this formula very well. And the energy carried will be J dot m dot times J. What is J? J equals E plus PV plus KE plus PE. The PV term comes from the work transfer, the flow work. Now, to simplify it further, E equals, it is E plus PV, which is E equals U plus KE plus PE plus PV. If we separate KE and PE, it becomes U plus PV, and this together, these are each thermodynamic property, U, P, and V, and is called H. So the formula becomes H plus KE plus PE. So kg per second, and each of these term has kilojoule per kg, which is kilowatt. So the energy carried by a flow in kilowatt is given by m dot times H plus KE plus PE. What is H? It is the enthalpy or specific enthalpy. Many a times people ask, what is enthalpy? And the standard answer is, oh, enthalpy is U plus PV. There is nothing wrong in that definition. U is the specific internal energy, P is the pressure, and small v is the specific volume. Each of them are thermodynamic property, and let me remind you, P, T, V, U, H, and S are very special. They are all thermodynamic property. That means any two of them will pin down an equilibrium. To identify the properties of fluid, if you know two of them, the others can be immediately calculated by some formula or other. So the J dot is called the rate of transport of flow energy. So the other meaning of enthalpy can be obtained immediately, because you can see that if KE and PE are not so significant, then H represents the energy carried by the flow per unit mass. In other words, if KE and PE are negligible, H equals J dot by M dot. So that gives a nice physical meaning to H, enthalpy. Okay, we can now put it all together and get what the energy equation looks like, get an expression for it. So the energy equation, you can see, in this case, the energy equation for an open system shown in the red boundary is given by the following equation, where the dEdt is the rate at which the energy, stored energy inside the system, is changing, increasing. dEdt is positive, means the energy inside is increasing, shown by this bubble here. Again, this you can show in this animation, go and check it out. The rate at which it is increasing, on the right hand side we are writing the reasons, is the summation of the rate at which energy is carried in by the flow minus the rate at which energy is coming out, plus the rate at which heat transfer is carrying energy into the system, minus the rate at which work transfer, external work transfer, is carrying the energy out. There is no other way energy can be changed in the system. So suppose it's a mass equation. Everybody understands mass equation. Mass going in and coming out, the difference must be accumulated. There is no other way. In case of energy, you can just think just like mass. It's a different entity, different property, but it's same way you can understand the energy equation. Energy is going in this case, two different ways. Mass is carrying energy, heat is carrying energy. Energy is going out in two different ways. And the balance equation shows that it accounts for all the ways in which energy can be accumulated inside. And there is no other way in which energy can be accounted for. So this is for any system. So when we apply it to a specific system, the energy equation can be simplified quite a bit, and we'll be applying this equation over and over to different kind of systems. Okay, let's get on now with the entropy equation. Entropy is very difficult to explain in a couple of minutes, but let me give it a shot. we understand energy. It cannot be destroyed. Suppose we have a system and it has some certain amount of energy. But energy equation never tells you how it will be distributed. In other words, if all the fast-moving molecules come to the left side and slow-moving molecules stay on the right side, a system can become hot on one side and cold on another side. But that doesn't happen. You don't go to a room and find half the room is hot, half the room is cold. So there may be some other fundamental principle that governs this sort of things. You don't find a system suddenly turn into hot and cold. On the other hand, you see something with hot and cold, you go back and you find everything became warm. Hot and cold destroyed each other. And that's where the second law comes from. And if you understand entropy equation, it's very easy to quantify, to put it into a mathematical formula. So what is entropy? Entropy is basically the number of ways, it's related to number of ways in which energy can be distributed amongst molecules, internal energy. Of course, the kinetic energy that we can see in our eyes, that's all molecules are moving at the same speed. There's only one way you distribute kinetic energy of the entire system. But the molecule's random motion, random energy the molecules possess, it can be distributed in so many ways. And entropy is simply a measure of that, the logarithm of that. So if a system has higher entropy, that simply means it can it can store the energy in more ways than a system which has low entropy. So suppose a system is so cold that its temperature is zero Kelvin. So that means what? That means that all the system, the ways in which you can store energy, because the molecules are not moving energy anymore. Kinetic energy of the systems is zero, and that's what means. So when molecules cannot move, it has only one way to store energy, and therefore the log of 1 is 0, entropy becomes 0 at 0 Kelvin. So as a matter of fact, it is easier to define entropy than energy. Think about it. You don't know what is zero energy. You can understand what is kinetic energy to be 0, potential energy to be 0, but what about the internal energy of the molecules? You never know when it is 0. Even if the molecules stop moving, there can be potential energy, right? Whenever there is a force between any two particles, there is a potential energy. That's the meaning of potential energy. So therefore, entropy is easier to actually understand and quantify. So to derive the entropy equation, you got to know how entropy can be transferred into a system. And of course, the first way is transport of entropy. As you can see, just like energy is carried by mass, entropy can be transported by mass, and it simply means entropy transfer rate is mass flow rate times entropy per unit mass. There is another way, fundamental way in which energy is transferred is by heat. So whenever heat is transferred, we know its energy is transferred, and it also means entropy is transferred. How much? Whatever is the heat transferred divided by the temperature of the boundary, and that's the entropy transfer. On the other hand, work transfer does not transfer any entropy, because work is an organized behavior. When say a shaft is turning, all the molecules are turning the same way. Whereas when heat is transferred, there is a lot of random collision between molecules to transfer heat. So that randomness, inherent randomness in heat transfer, causes entropy to be transferred with heat, whereas with work transfer, there is no entropy transfer. And finally, unlike mass and energy, which cannot be destroyed or created, entropy can be created. And what is magic about entropy is that the entropy creation is a measure of friction. Again, let me quickly explain what I mean by that. Whenever you see a difference getting destroyed, which nature has a tendency to do, whenever you see a hot thing next to cold thing, you know intuitively that something will happen so that the hot thing will try to become cold and the cold thing will try to become warm. You see that in nature so much. Suppose I drop a a drop of ink in water, you know that ink is going to diffuse. In other words, the concentration, high concentration of ink and low concentration of ink will not stay put together forever. There will be a way in which nature will destroy the difference. Whenever there is you rub your two hands and nature doesn't like it, it tries to stop it by causing friction. Friction always opposes velocity gradient. So these kind of things in nature is called thermodynamic friction, generalizing it. And whenever there is friction, you can show that entropy is generated. So this S dot gen terms is a measure of entropy generation, is a measure of friction inside the system. And that's what makes engineers use the second law so much. Not for its esoteric reason, not because it gives the direction of time. It is used in sociology and so many other different fields. No, because entropy is created, generated whenever we see friction. So imagine if we have a machine, we have an engine that has a lot of friction versus a machine that we want to build which has very little friction. So entropy generation will connect us. Ideal machine will simply set S dot gen to be 0. And when S dot gen is 0, that means the machine will become almost perfect, no friction. Another thing is that this frictionless device we call reversible. Why? Because if entropy is not generated, then whatever you did, you can reverse and there will be no footprint. Because in most natural phenomenon, a gradient gets destroyed. So anytime a gradient destruction takes place, it means this implies S dot gen is greater than 0. So if you see a temperature difference is getting destroyed, there's heat transfer, there'll be gradient destruction, S dot gen. So if S dot gen equals 0, in other words, this is the best way in which you can carry out many different processes. That's how we'll figure out the most efficient engine. So this will have a whole lot of application in the coming series of modules. So now we can put it all together. Again, you can go to this animation or read chapter 2 to take a look at how entropy equation is derived. So here again, the red dashed line is our system, our abstract system here. Entropy, whenever mass goes in, carries entropy. Whenever mass comes out, it carries entropy out. As we saw, whenever heat is transferred, it carries entropy. And finally, entropy can be generated because of friction. So these 4 different reasons is why entropy in the system changes. That's shown in the left hand side, ds dt, the rate at which entropy of the system increases, equals the rate at which it is coming in by mass, transported out by mass, plus entropy entering by heat, and entropy that is generated. So it's just like bookkeeping, just like you keep track of your money. Assuming you do, you can see the money in the bank changes at this rate, and because of different reason, it's nothing different. So try to understand mass, energy, and entropy in the light of the balance equation, because that's how we're going to be applying them all the time. So instead of fighting over each quantity alone, put them together, juxtapose all of these governing equation, mass equation, energy equation, entropy equation, and let's write them down. Then you will see their similarity amongst them, and as we simplify them, you will see how similarly we do that across the board. This is our mass equation. Each term is in kg per second. This is our energy equation, and the unit is kilowatt, and And the unit here would be, look at the easiest term, Q dot is in kilowatt and TB is in Kelvin. So this is the unit of the entropy equation. One quick note, if a system is steady, you know the mass of the system will not change, energy of the system will not change, entropy of the system will not change, because how do you say that? Steady by definition means the entire system, if I have a system, open system, mass is going in, mass coming out, you name it, heat going in, and maybe work is coming out in different form. But if a system is hot here, if a system is very hot on this side, and suppose the system is very cold on this side, then the idea of a steady system is that if it is hot here, it will always remain hot here. If it's cold here, it is always cold here. So as a result, look at this. If it's a steady system, if somebody says, what will happen to the mass of the system? The answer is that if it's steady, then the mass of the system cannot change. Even if new mass goes in, some mass must be coming out because the picture is not changing, right? So think like this. What does dmdt means? Mass of the system at time t, and then you find mass of the system as time t plus delta t. You subtract the two, find the difference, and divide by delta t, right? That's the definition of the derivative. So if the system itself is not changing, how can mt and mt plus delta t can be different, right? If everything about the system is the same with time, then at every pixel the mass is the same, so therefore entire system mass cannot change. Same with energy, same with entropy. So when we have a steady system, this goes out, and this goes out. It's a big simplification. And of course, if the system is closed, you understand there is no mass going in, mass going out, mass going in, no mass going out. If a system is adiabatic, which means there is no heat transfer, this term will drop out. So likewise, we will have a lot of simplification that we'll use, but this is the set of equation that can be the starting point for any type of analysis in thermodynamics.